Here's a simple circuit. We have two resistors in series and they have the same resistance. So let me ask a question. Which resistor uses up more of the EMF? That's a trick question. They use up the same amount. Each uses half of the EMF, and the reason is because each one contributes half of the circuit's total resistance. The total resistance is 10 ohms, and this contributes half of the 10. Likewise, this contributes half of the 10, so each gets half of the EMF. We're going to make these variable resistors by drawing arrows through them, and that basically means we can change the value of the resistance. We could make the bottom resistor big, or we could make the top resistor big, or make them equal. When the bottom resistor is big, which resistor uses more of the EMF? Well, the EMF is divided between the two, and the bigger the resistance, the more share it gets. So this resistor contributes 9 ohms out of 10 total, so it will consume 90% of the EMF. Now, this bottom resistor only consumes 10% of the EMF because it contributes 10% of the total resistance. One of the ways we can draw this is by putting a box around the two resistors, and we put an arrow pointing to the split between the two. When we move that arrow down, the bottom resistance is really small because there's not much there. When we move the arrow up, the bottom resistance gets really big because there's a lot of material there. There's a device that actually does this, and it looks like this even. It's called a potentiometer, and it has a simple slide which moves up and down. The slide is the arrow, and when we move it up, the bottom resistance is big. When you move it down like this, the bottom resistance is really small. And this is the same sort of thing you see in light switches that have dimming features. Those are potentiometers. So here's how you draw a potentiometer in a circuit diagram. You do not show the two resistors. Instead, you simply draw the box with the arrow. And we don't even always write the two resistance values. Sometimes we'll just show the arrow. Whenever you put the arrow up or down, you change the bottom resistor. When you push the arrow down, the slide is low, and so there's not much resistance on bottom, and it doesn't get much of the EMF. When you push the slide up, there's a big resistance on bottom, so it consumes a lot of the EMF. Now we're going to connect another device in parallel with the bottom. So how do we draw that over here? You simply connect to that arrow. The arrow here does not show which way current is going. Current is flowing out of here. It's passing into the potentiometer. It splits. Some goes this way, opposite the arrow. The rest goes down this way. The same exact scenario as what you see on the left. There's a junction where the current splits, and then it joins back up at the bottom, right here. Okay, so let's say that we want to make our battery 10 volts of EMF, and we put the potentiometer at the very top. Does this consume 10 volts or 0 volts? Well, it's in parallel with the bottom resistor. It's in parallel with the bottom resistor. And the bottom resistor is huge, so it gets all 10 volts. When you put the slide at the bottom, now the bottom resistance is 0. All of the resistance is on top. So the bottom has 0 volts of potential difference. And this has 0 volts too, because it's in parallel with the bottom resistor. Why is this so useful to us? Well, take your EMF, your cell, connect the potentiometer, connect the device, and now you can inspect this device. Put an ammeter in series and a voltmeter in parallel. What we're going to do is we're going to move the slide up and down, and as we do, we are changing the potential difference across this guy right here. The potential difference changes because we're adjusting the bottom resistance. And as we adjust the bottom resistance, we change how much of a share it gets of the EMF. Each time we measure the voltage, we also measure the current, and we can see how does current change when we adjust that potential difference. Some devices make a straight line through the origin. That means that they're ohmic, or they have a constant resistance. Some devices make a graph like this, which means they're non-ohmic. The resistance is actually increasing. What is this business of calling something ohmic or non-ohmic? You have to remember Ohm's law, and this is something to memorize. Ohm's law states that the resistance of a device is constant, even as the potential difference across the device changes, assuming the device is kept at a constant temperature. Only certain devices follow this law, and those which don't follow the law are non-ohmic.